In this video, we're going to talk about relative acid and base strength. Now that we've talked about how we kind of evaluate it qualitatively using hydronium ion concentrations. So let's start with acid strength. In general, when we talk about an acid being strong, we are talking about a measure of its ability to transfer a proton. So the more protons are transferred from a sample, the more acidic it is. And so it means that it is being an electrolyte. It means also that a strong acid is going to have an equilibrium constant that favors the products if we're talking about the reaction being breaking that bond to the hydrogen. So in general, we see that strong acids are strong electrolytes and they completely ionize. And so what I mean by ionize, I mean that like in the example of hydrochloric acid, that bond completely breaks in all of my hydrochloric acid molecules. And I really have, once it's in water, H plus and Cl minus. They also react completely with water, meaning again that bond breaks. And so both of these are trying to say the same thing, that bond breaks and we have ions at the end of this reaction. We add it to water. Some great examples are hydrochloric acid, also nitric acid. Now, weak acids are not going to completely transfer or break all of their bonds to their acidic hydrogens. And so this will just be a partial reaction. So it's going to have an equilibrium constant that's smaller, or one that maybe favors reactants. It'll be a weak electrolyte as well. And so we'll see that it'll be less than completely ionized. So that means that when I put one of these weak acids like acetic acid or formic acid into a beaker, that some of my acid molecules donate a hydrogen and some do not. So only a percentage will. Whereas that strong acid, all of them will donate their hydrogen once they touch the water. And so here's a pictorial representation of this. We have our strong acid right here, and we have a weak acid on the right. And so you can see within our weak acid that some of our hydrofluoric acid molecules are still intact. And then we have some of them have dissociated, where we have F minus ions and then H3O plus. And so only some of these HF weak acid ions have actually dissociated or transferred their hydrogen or donated their hydrogen or broken the bond between the hydrogen and the fluorine. There's a lot of ways to say this. Now, our strong acid, when you look at it, it's going to show that all of our ions are going to be dissociated, which is one way to say it, which means they ionize, or that all of our protons have been transferred. As you can see, we don't have any HCl molecules in solution at all. We only have our H3O plus and our chloride ions. And so all of that HCl has broken apart into hydronium and chloride ions. So looking then at the strength of a base, it's really a measure of its ability to accept a hydrogen. So similar to acids, strong bases are going to be strong electrolytes. They're going to completely react with the water. An example would be hydroxide ions. These are really common, or things that have multiple hydroxide ions. A very strong one would be oxide ion as well. Then we also have weak bases, like weak acids. They're going to not be a strong electrolyte. They're not going to completely react with water. Examples of this are like ammonia. That's a really good one. And so we can see that. So for something like sodium hydroxide, when it goes into solution, it'll completely break apart. We'll have all hydroxide ions for any sodium hydroxide that went in. Whereas for our ammonium, when this is dissolved in water, we have some hydroxide ions that form an NH4 plus, which would be the conjugate acid. But we have some of our ions our ammonia molecules staying intact, meaning it doesn't completely react with the water. Not all of my NH3 molecules will accept a hydrogen, just a percentage of them. And that's what makes it a weak base versus a strong base. Here's a handy chart just for reference, really, kind of give us some context about relative acid strength. And so there's really only a few I think it's 6, and I'm only seeing 5 listed here. Um, Only a handful of really what I would consider strong acids, ones that we're going to assume dissociate completely, or they dissociate enough that we can assume that they have equilibrium constants that are larger than 1, that they favor products. So nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid are strong acids. And that means we're going to assume that they completely break, all donate that hydrogen, they completely break that bond. So we assume they all dissociate 100%. Now, hydronium ion is pretty strong, but it's not going to 100% break apart. And so then that's kind of our benchmark between our strong and our weak acids. And then we have lots of weak acids, lots. And here's just a few examples, like phosphoric acid, hydrofluoric acid, acetic acid, carbonic acid, the ammonium ion, which is the conjugate acid of a base, right? So this ammonium ion right here, we're used to seeing this after ammonium reacts with water. And so what we see here is that we have this increasing acid strength as we go up. So where we have really weak acids here at the bottom and strong at the top. And we'll notice that if we look at the conjugate base of these weak acids have stronger conjugate bases. And so something like a strong base like hydroxide ion is going to have a very weak acid conjugate acid. Ammonium is going to be strongish. It's going to still be a weaker of the bases, but it's going to have a relatively weak acid as its conjugate acid. So bases that are very terrible bases that are just weak bases are things like the iodine ion or bromide ion or chloride ion, or all of the conjugate bases of strong acids. Because for them to accept a proton, they're going to form a strong acid. But we've just told you that the acid is so strong, you can assume that it always donates its protons. So the second it form, it would just form that base right back. So it doesn't really happen. And so this is something that we're going to see, this theme that any sort of strong acid, its conjugate base will be very weak, and a strong base will have a very weak conjugate acid. And so here we're putting this written out. So again, our stronger acids and bases are going to react to produce weaker conjugates. So again, that stronger bronzed acid has a weaker conjugate base, and the opposite for a weak acid will have a stronger conjugate base. All right, I like this graphic to show this concept a little bit more. It's showing how when we have really strong strong bases, we're either going to form when it undergoes a reaction with water, right, where it accepts a hydrogen, it's either going to form another strong base still, or something that's a very weak acid like water, right? Where we have these really strong acids, when they actually react, so when they are added to water, they're going to form neutral conjugate bases, things that aren't actually going to be a base. They're so weak. But most of what we're looking at, like these are just a few of like strong bases and strong acids that we actually have. Most everything is weak, right? And so we're going to have these weak acids that form weak base conjugate bases, and weak bases that form weak conjugate acids. And that's going to be the majority of what we're looking at with different acids in the lab, like of just all the ones out there. And so, well, I don't feel that you need to memorize the strong or the weak acids and bases, especially you don't need to memorize the strong ones. The hydroxide ones are just, you're going to see them so often, it'll be easy to remember. And the strong acids, I think there's really, 6 total at most. And so they're worth knowing. So that way, if you ever see them on a bottle, you're like, whew, that, beware. But by no means do you need to do that.